Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll give a demonstration of machine learning component framework with Tensorflow Playground. We'll give an overview of Tensorflow Playground in this video. The Tensorflow Playground can be accessed from the following URL: playground.tensorflow.org. It is built in JavaScript. It provides a way to visualize machine learning training. It allows changing different components like training data, model, loss function to some extent, and parameters of the optimization algorithm. The evaluation protocol is, however, fixed. The playground was built for experimentation with neural networks visually, but we'll repurpose it for understanding various important concepts in machine learning. It will be used to highlight components of machine learning framework and visually demonstrate how machine learning works. I have used this tool to introduce machine learning to many of my students, and they found this extremely useful in developing their understanding about machine learning. So play with it freely without fear of breaking anything down. It's a browser-based system, so any changes that you do, it won't affect the system permanently, but it will give you a richer experience of understanding how machine learning training responds to different configurations. So this is how TensorFlow Playground looks like, except for the bounding boxes that we have drawn to showcase or to label different components. So we have training data on the left pane, then we have model, we have a loss function here, then optimization procedure, a small area to visualize the evaluation metrics, and a place to visualize the model that was learned. So specifically, we show the playground shows the boundary between two classes as model is learning it while undergoing the training process. This is called the decision boundary, which separates two classes, blues and oranges. And this box essentially also shows us the inference that model is drawing on the test set. Each of these component has multiple configuration parameters that we can vary and study its effect on the training data. Let's look at each of these component separately and in detailed manner. The first component is, of course, the training data. It is the most important machine learning component. As you know by now, without training data, we cannot train a machine learning model. In TensorFlow Playground, we have data with two classes, positive and negative classes. The examples from positive class are represented with blue color, and the ones from the negative class are represented with orange color. The playground provides different permutations of training data. So there is one setting where we have the training data in such a way that two classes are linearly separable. That means we can draw a line as a boundary separating two classes. So these two classes can be separated by a line. Then we have another data set where two classes are separated by a circular decision boundary. So in the last data set, line was enough. Here line won't work. So we need to construct a circular decision boundary in order to separate these two classes. Then we have even more complicated setup where the classes are distributed according to XOR, right? They are kind of very complex decision boundary that needs to be learned in order to separate two classes. And even more complicated one where the classes are separated on a curvilinear path. So this is even more complex data set to learn the decision boundary. So depending on what you want to explore, you can select one of these data types and see its effect on the model that is getting trained for a given configuration of other components in the framework. We can also control the noise in the training set. If you increase the noise, the training points starts getting distributed across classes. So there will be some kind of a noise. So the points from positive class will appear in the area that is predominantly belonging to the negative class and vice versa. Each data point has two features, x1 and x2. We will typically set 80% examples as training and 20% examples as test, which is a general way of distributing the training examples in machine learning. We will be using a classification model because we have two classes, or in other words, the labels are coming from a set containing two values, which is positive and negative. So we need to use a classification algorithm, and the basic classification algorithm is logistic regression, which we'll be using for this demonstration. And as you know, the model maps the features to the classes, and here we are interested in training the model such that it maps features to the classes as accurately as possible. In other words, we are interested in learning weights that are given to the feature by the model. So there is a weight associated with every feature, and Tensorflow Playground visually demonstrate how important is the feature. So if the feature has a larger weight, the line will appear as a thicker line, and if the feature is not so important, the line will be a thinner line compared to the other line. Okay, so you can see that here the weight that is assigned to x1 is 1, so it's a thinner line compared to x2 where the assigned weight is 4.3. Right, so what is happening is this x1 and x2 are essentially getting into the classifier, which is a logistic regression classifier, which learns the decision boundary separating these two classes. This is a linear separator that will be learned by the model, and we get a very nice color coding of the region across two sides of the decision boundary. So darker the color, higher the confidence, higher is the confidence of our model in its prediction. We cannot explicitly specify loss function in TensorFlow Playground. It changes with the type of the problem. For classification, it uses a loss called binary cross entropy loss, which we will study later in the course. And then there is another parameter that controls the loss function, which is called regularization, and its type and rate, however, can be adjusted. We will study regularization again in the second module of the course while studying linear regression, and regularization will be appearing many times in the course. So it's a very general concept in machine learning. So do not worry about it right now. We'll study it in due course of time. And finally, the optimization procedure. We have a fair amount of control in optimization procedure. So you can see three control buttons here. The one in the middle is the most important one that helps us to start and pause the training. The one on the left helps us to reset the model parameter, and one on the right helps us to go through the training process step by step. Okay, here we can set the number of epochs, and here we can set the learning rate of the model. As we start training, with every epoch we get a new model, or we get new weights to the respective features, right? So the weights are corresponding to the feature, and as we train the model, with every epoch we get different weights. And because of these particular weight values, we also see different losses that appear in this region, which is the evaluation visualization region. Okay. So as we move to the third epoch, the weight has changed, right? So if you go back and check, the weight was 0.19 here and 0.56 over here, and after in the next epoch it had changed to 0.23 and 0.59, and the losses have also changed. Evaluation procedure evaluates the goodness of the model with an evaluation protocol. The playground uses only training and test loss for evaluation. There is no scope for any customization or selection of the sets. And as the training proceeds, we get to see changes in the test and training loss. Why? Because as the training proceeds, we get new weights, and because of new weights, we get different predictions that result into different losses. And we have also studied this in the previous video while looking at a bigger picture of a machine learning component framework. When the model is getting trained, both the losses should gradually decrease. Okay, so this is a good sign. So this is a good sign that your model is getting trained properly. The losses should gradually decrease, and at the end of the training, both training and test loss should be small. The rate of decrease is proportional to the learning rate. This is another picture where instead of reducing, the losses are actually increasing. And if this is happening, this is not a good sign. This means that the model is not training properly. And this could happen because the learning rate is too high, or there are not many informative features describing the training examples. If the model is getting trained properly, both the training and test loss should go down, and both of them should be close to zero at the end of the training process. So let's take a tour of TensorFlow Playground now that you are familiar with different components of the TensorFlow Playground. When you open the TensorFlow Playground by typing playground.tensorflow.org in your browser, you get such a window here. Right? So there is a network-like structure over here. What we will do is, this is basically a neural network. We are yet to study this particular thing. So what we will do is, we will simplify a model by removing this particular network and restoring it to a state that we saw in our presentation. We will select a simple setting of training data where two classes are linearly separable, positive classes and negative classes. We'll use 80% examples for training and 20% example for test. We have set the noise to the 0 and we have used batch size of 10. Now if you change the noise setting, you can see that some points from blue class are crossing over to the red class as we increase the noise, right? So if I make noise of, let's say, 45%, you can see that there are some blues and whites have crossed over. Okay, and then what you can also do is, you can look at the test data and see how these points are also scattered across the decision boundary. But if I make the noise to 0, even the test data, there won't be any crossover in territory of each other. Okay. So right now we'll select a simple setting of 0 noise and a linearly separable classes. Okay, so we have two features, x1 and x2. We talked about them. So every data point is represented by two features, x1 and x2. And this is the optimization procedure. So right now we have not trained the model, so it is at 0th epoch. We'll select the learning rate of 0.01. We'll use sigmoid activation function so that we get a logistic regression classifier, and we do not use any regularization here. That's why regularization is none and the regularization rate is 0. Here we can select the problem type, and we have selected the problem type as classification. You can also select regression as a problem type, but for this demonstration we are using classification as a problem type. Now what we will do is, we'll first press this regenerate button and regenerate the training data. So we have regenerated the training data and we will now start training the model. Okay. So when we start training the model, what happens is that initially there will be some kind of random weight values assigned to the weights. Let's look at them. They are 0.13 and 0.081. Because of these random values, we still have a model with some random values assigned, and because of that we get some test loss and the training loss, and which are fairly high numbers right now because we have not trained the model and these are just randomly initialized weights. Now what we will do is, we will make one step of epoch and you can see that the weights have changed. This has become 0.28 and this has become 0.25, and the losses have also reduced substantially, right? So now we'll make one more step, and we can see that the losses have gone down even further, and the weights here have also changed. Okay, and you can also notice that we have a new decision boundary here. Loss has decreased a bit, the decision boundary has also changed a bit, and you can see now as we take steps at 6th epoch, the loss has even reduced further, the weights have changed, and the boundary is now slowly shifting. There is not much change that we can observe in the decision boundary. So you can see it is getting further reduced, and now it has reduced. It is very close to zero. It is not exactly zero, but very close to zero. Training loss and test loss are again low and close to each other, and you can see that the loss has smoothly decreased, right? And at the end of the training, both the losses are close to zero. This is the decision boundary. Across the decision boundaries, classes are also getting separated correctly, right? So all blues are in their own region and all oranges are in their respective region, right? So if you look at the test data, so test data is also correctly separated. All blues are in blues region and all oranges are in the orange region. Okay, so it took us some 18 epochs to reach to this particular level. Now what you can do is you can change the learning rate. So let's say we make it very small. Okay, and now we will reset the training. So after resetting the training, you can see that the weights have reset to some random values and the losses have also reset to some values because of these weights, right? So because of these weights, we have a model, and model makes prediction based on which the losses are calculated. So these losses are also high because of the randomly initialized weight. Now what we'll do is we'll essentially start the training. Instead of stepping through the training, we'll start it. And because we have learning rate which is way smaller than what we had earlier, we expect to take longer to get the decision boundary. So now you need to watch out on these loss values, what is happening to them, then also decision boundary, how it changes, and the weights, right? So you will be able to see the losses and decision boundary directly, and weights. In order to see the weights, you'll have to hover over these lines. Okay, so let's train. Let's start the training. You can see that the losses are decreasing slowly and the decision boundary is also changing, right? So right now we started with oranges in the blue part and vice versa. Now we are seeing the change in the decision boundary and losses are also gradually reducing, right? So you can see the change in the decision boundary, and it has taken us almost 450 epochs to reach to this level, which earlier we reached just within 18 epochs. So now you can see that after almost 600 epochs, we are still not close to what we were there in 18 epochs with learning rate of 0.01, right? Yeah, so let's wait to get to the levels of the previous learning rate and we'll note down how many epochs it took us. Now the training is progressing really slowly. You can see that the losses are reducing fairly slowly. So it will take longer time, right? So it has already taken us more than 1000 epochs. So what we'll do is we'll stop this and we'll look at one more setting, okay? So in the third setting, what we'll do is we'll increase the learning rate to, let's say, 0.3. We'll reset this training. You can see that the weights have reset to some values and the losses have also reset due to this random initialization of the weights, and we have a decision boundary which is again due to this random weight initialization. Okay, so let's start training this model. Instead of training this will finish pretty quickly. So it has gone to 0 in no time. So what we will do is, in order to understand exactly how many epochs it takes, we will actually step through the training process, right? So but you can see that, you know, even after increasing the learning rate, we are able to learn the decision boundary fairly accurately, and of course quickly, because we now have larger learning rate, and learning rate basically helps us to decide how fast we are learning, right? So if the rate is larger, we'll learn faster, and if the rate is smaller, we will take baby steps towards the optimal solution. Okay, so I'll reset this again. Again, you can see that the weights have reset to some random values, and so are the losses, and now we'll start stepping through. You can see that the first epoch itself has got the losses significantly down and very close to zero, right? So one more epoch probably, and yeah, test loss has already become zero, right, in the third epoch, and you can see the weights of 0.76 and 0.62 after just 3 epochs, right? So if I make it, if I further increase it, we'll reset this again and we'll start stepping through. In the first epoch itself, we got the losses down to zero. But I would warn you about setting very high learning rate. It doesn't guarantee that will converge always very fast. There is a chance that if you have learning rate too high, we might overshoot the optimal solution, and we may not be able to get the optimal solution at all if your learning rate is very high. Okay, so I would urge you to explore this playground and try various data sets and various parameters here, and experience the machine learning training part visually. I hope you enjoyed this session and you now have a better idea how machine learning model is getting trained with different learning rate, and how the weights change and how the decision boundary changes with every training epoch. We'll be coming back to this playground many times during this course, and where we will also look at other kinds of data sets that are available here, and we'll see some very interesting properties of model training when we'll visit those data sets. Until then, happy learning machine learning. See you in the next video. Namaste.